Okay, everybody. I wanted to take a second to regroup because I could feel myself kind of getting away from my explanation, and I want to bring it back around, keep everything as simple as possible. So I'm going to break this into little parts and chunks to make it easily digestible. Don't be intimidated by any of this math. It's super easy. Okay, so I kind of want to go back a little bit, back about one slide, to just refresh our memories. So here, this little bit here was a review. I went back through our sickle cell lab to show you how you might use some of the techniques that we've talked about to get direct information about people's genotypic makeup. So here we had two heterozygotes, the mom and the dad. We had a homozygote in the brother and a homozygote in the sister, right? And hopefully you remember how I derived all of that. So the point of this is, the take-home message is, there are ways to go out and get direct genetic information about people. You can either sequence their genes, you can do an analysis like this. Sometimes you can tell by looking at them what their genetic makeup is, like for blue eyes, or if someone has a particular disease, then you know what their genetic makeup is. So in this example, I said, okay, let's pretend that we went out and we took a really good random sample of people. And we're going to say that this is a random sample of students at FMU, okay? That these are FMU students. So we have 190 FMU students. We went out, we collected their DNA, and we did this analysis. So we have direct information about their genotypes. And when we did that, we found that 135 of them we're going to say this is homozygous dominant because these are two functional copies of the allele, right? We're going to say that this is heterozygous because we have one of each allele. And we're going to say that this is homozygous recessive because we have two diseased or non-functioning copies of the allele. Now, it's important to remember that in this scenario that I'm giving you, we're talking about a system with two alleles. Okay, there's not a third allele here out in the population. So only two alleles are possible. And so because we knew that 135 people had this particular genotype, we knew that we sampled 190 people, we were able to take that information and calculate the frequency with which you would encounter this genotype. So our frequency was simply 135 divided by 190, which came out to be 0.710. And you can repeat that process for these. So why is that relevant if you were a population geneticist? Well, now that you have taken this sample, you can make estimates about the larger population. So I have this sample, but that's not everyone at FMU. It turns out that the student body at FMU is roughly 4,000 students. So if I wanted to know how many of the 4,000 students were likely to be homozygous dominant, I would just take my number 4,000 and multiply it by the frequency that I have estimated here, which is 0.710. And that gives me, let's see here, 2840 students that I would expect to fall into this category. Now, perhaps you're more interested in knowing how many students at FMU you estimate would have sickle cell disease. Well, we can just undergo the same process. We know that we have 4,000 students at FMU, and we estimate the frequency based on our random sample. We estimate that that's the frequency of this genotype. So we might guesstimate that somewhere around 232 individuals at FMU would have sickle cell disease. Okay, so that gives you an idea of how population geneticists might use this information. We were also able to take this information and do some calculations and derive the allele frequencies, okay? You need to remember how to do that. Go back and watch the first video. But here we have a frequency of 0.826 for the functional allele and a frequency of 0.174 for the diseased allele. And because there's only two possibilities, we only have two alleles, these two numbers add up to 1. So I want you guys to kind of stick a pin in this. We're going to use this information in just a second when we start talking about Hardy-Weinberg equilibrium, okay? And that's where we left off at the end of the last lecture, was in talking about Hardy-Weinberg equilibrium. And I introduced it in terms of this Punnett square in thinking about maybe what a dihybrid cross would look like. But I want you to kind of back up a little bit. And instead of thinking about this as a dihybrid cross, I want you to think about it as a population now of individuals where there are two possibilities. There's two alleles. You can either have this dominant allele or you can have this recessive allele. And you can have this dominant or you can have this recessive. And if that's what we have out in the population, then we can, and these guys are randomly mating, then we can expect 4 different outcomes to occur, right? You can either be this, right? So we're just going to call that A squared. You could be that. 2 different ways you can be this, because you could really, we say it's A, and then this would be A, right? But 2 different ways you could be a heterozygote. So we're going to do 2AA, okay? And then there's one way you can be that. Oops, let me take that off. I want to make that square. Okay, so there's one way you can be that. And if we add all of these up together, that's all the possibilities. So the frequency with which all 3 of these, or actually all 4 of these things would happen at once would be 1, wouldn't it? Okay, so that's how we derive this Hardy-Weinberg equilibrium equation. Now, Hardy-Weinberg don't use, or they didn't use, A's and whatever, because it got a little confusing. So by convention, population geneticists call the dominant allele P, so P squared plus 2PQ is what we're going to call the recessive allele, plus Q squared. If you add all of those up, that's the entirety of the possibilities that you would have in a 2 allele system, okay? So we can actually use this to do a couple things. So we can use this equation to help us understand basically what our gene pool looks like. We can use it to kind of get some information about our gene pool, and we can use it to predict what would happen after people start reproducing, or individuals start reproducing in this gene pool. Is it going to have an effect on our genotypic and allelic frequencies? Well, we can use this equation to tell us something about those 2 things. Let me give you an example. So in this situation, we had all the information because we actually went out and we did a genetic analysis to get this information. But you guys know that in real life, that's likely not going to be something we can do. We can't just go out into the population and just start doing these random genetic tests. But if we have a situation where maybe we have a disease, right, and the disease is recessive, then we start knowing something about our alleles. Let me give you an example of what I mean. Let's talk about cystic fibrosis, which I'm going to abbreviate CF. So cystic fibrosis is a disease of your respiratory tract. It has to do with chloride channels, but we're not going to worry about the physiology of the disease right now. Instead, I just want you to know it's a disease where you get a whole bunch of really thick, viscous mucus in your lungs, and it occludes your lungs, and you have respiratory failure. It also can mess with your digestion, but ultimately people die of respiratory failure with this disease. It's a genetic disease, and the allele that causes the disease is recessive. So if you have 2 copies of the gene for cystic fibrosis, which, let's see here, let's just make things easy peasy for ourselves. Let's use a big N for normal, for dominant, and we'll use a little n for the disease, okay, for cystic fibrosis. So if you have cystic fibrosis, there's only one genotype you can be. You can only be NN, because it turns out all you need is 1 functional copy of the gene in order to be okay. So if you have this disease, we know that is your genetic makeup. So if you present to a physician and you have cystic fibrosis, we automatically know your genetic makeup. And through studies of cystic fibrosis patients, we know that 1 in 2,000 people in the US has cystic fibrosis. That means that 1 in 2,000 people is this. Does that make sense? Let's go back to our equation. So we have P squared, which is our dominant. So that's like a homozygous dominant situation. These are our heterozygotes. And this is our homozygous recessive situation, okay? So if we know that 1 in 2,000 individuals has cystic fibrosis, that's the same thing as knowing that 1 in 2,000 individuals is little n, or Q squared. They are homozygous recessive. So now we can calculate some stuff. Well, if we divide 1 by 2,000, we get this number. You can double check my math, make sure I'm not lying to you. So Q squared is 0.0005. Huh. Well, now I have enough information to know everything else I want to know about this population. Well, what do you mean? Let me show you. All right, well, what if I took the square root of this? That would give me Q, wouldn't it? If I wanted to get Q from Q squared, all I do is take the square root of that. That's going to give me the frequency of this Q allele, isn't it? Okay, so let's go ahead and do that. And if you take the square root of 0.0005, it is something like 0.002. Let me make sure that that's correct. Yes, okay. So in other words, 20% of the alleles in our population are the cystic fibrosis alleles. Well, if we know that the population only has 2 alleles, then we know that the frequency of big N plus the frequency of little n must be equal to 1. Or, to put it in terms of Hardy-Weinberg, P plus Q must equal 1. Well, now I know Q. So do I know P? Of course I do. P must therefore be 0.98. I hope you guys can see how I got that. 0.98 plus 0.02 equals 1, right? And that's all the alleles we can have as a dominant and a recessive, because we're only talking about a 2 allele system. Well, now I can use this information to calculate this, and I will know how many I can expect in our population to be homozygous dominant, how many I can expect in our population to be heterozygous, and how many I can expect, well, we already know how many are going to be homozygous recessive. So let's figure this out. So to figure out our number of homozygous dominants, all we need to do is get 0.098 and square it. To figure out our heterozygotes, we will times 2, we will multiply 0.98 times 0.02. And then, of course, we've already done this, but I'll go ahead and include it. 0.02 squared. P squared plus 2PQ plus Q squared, okay? Now let's go ahead and work out this math. I have it worked out somewhere already. Okay, so then this becomes 0.96. This becomes 0.039. Oops, I think it's 392. And then this becomes 0.0005. And then let me add all that up and make sure that adds up to 1 to make sure that I did my math correctly. Pretty sure I did. Let's see here. 0.98 plus 0.0392 plus 0.0005. Yeah, it comes out to just a little over 1 because of some rounding error, but that is correct. So now I know that 96% of the population are homozygous dominant, okay? And you can figure out the rest of these. So we know something about the prevalence of the disease. We know something how the disease might spread, okay? So that's one thing we can do with the Hardy-Weinberg law, is use these proportions to figure out information when we don't have the benefit of running a genetic analysis like this, okay? Now, another thing we can use Hardy-Weinberg equilibrium to tell us is whether or not a population is actually in equilibrium. And what do I mean by that? Whether or not a population is actively evolving. If it's in equilibrium, we're going to say that it's not actively evolving. Okay, so it turns out that this equation here, where we are assuming that there's two alleles in the population and all, if there's random mating, then this is what we end up with. But there are some assumptions built into the derivation of this equation, okay? So the first one I mentioned is we're assuming that there is random mating. Okay. We are also assuming a large population. We are also assuming that there's no migration into or out of this population, bringing in other alleles or more of one or the other alleles. So we're going to assume that there is no migration. We're going to assume that there's no mutation, because mutation might introduce a third allele or something, right? Mess up our calculations. So we're going to assume that there is no mutation. And lastly, we're going to assume that there's no natural selection. So in other words, for this equation, for p squared plus 2pq plus q squared to be true, then these 5 things must also be true. Because if we had natural selection going on and like these individuals were dying off or something like that, that would shift everything, wouldn't it? So basically, we can use this equation to make 2 predictions. First of all, if all 5 of these things are true, then what we can say is that, first of all, let me make sure I get my wording right here because I don't want to confuse you guys. First of all, the allelic frequencies of a population will not change. Not change. Okay, so in other words, let me go back up here. So basically, we will assume that these frequencies would stay the same as long as there's no mutation, as long as there's no migration into or out of our school, as long as our population is large and we're randomly mating, then these frequencies would stay the same and they would be described by this equation, okay? The other thing is that the genotypes becomes, or the genotypic frequencies becomes stable or steady after 1 round of mating. In your homework, there is a great animation that explains this. Okay. So in other words, back up here, after we go through 1 round of mating, these genotypic frequencies should be stable. So again, this equation is describing this situation. That's why we call it an equilibrium. It's kind of just hanging out, doing its thing. If we start deviating from this, if we see deviations from this equation, then we can assume that one of these things is going on, which means a population is evolving. So what we can do is we can take our calculation, our Hardy-Weinberg equation, and calculate what we think should be going on and compare it to the genotypic frequencies we actually see. And if our observed is different than our expected, then we know that something funny is going on, and it's probably one of these 5 things. Okay, so we can use this equation to tell us whether or not changes are happening. Now, this should sound somewhat familiar when you're trying to figure out whether your observed data matches your expected data. We did a lab like this, where we did something called a chi-square analysis to look at observed versus expected data. So let's go through. This is the table that I gave you earlier. I've just typed everything in. So see, that table made much neater. Okay, so let me make sure I have all my numbers ready because I'm going to do some math with you guys. All right, so okay, so we know that these are our allelic frequencies. We calculated that, okay? Now let's go through and let's do our Hardy-Weinberg equilibrium equation using these numbers in our calculation, okay? So p squared, if we take this, okay, and we say 0.826 squared plus 2 times 0.826, 0.174 plus 0.17, oops, 7. 0.174 squared. Now let's work out these numbers. Okay, so p squared should be 0.683. Okay, well, you know what? This p squared is a frequency. This is the p squared we observed. This is the p squared we expected. A little different, isn't it? All right, let's go ahead and calculate this one. The 2pq comes out to be 0.287. All right, that's a frequency. Look at this frequency. Compare it to this frequency. Not quite the same, is it? All right, let's do another. Okay. 0.174 squared works out to be 0.03. Again, these look different. Let's multiply these by 190 to see what we should, if our population was what we expected it to be, from Hardy-Weinberg equilibrium, then let's just see how these numbers work out. So let's take 0.683 and multiply it times 190 to see how many individuals we should have had if our population was in Hardy-Weinberg equilibrium, okay? And that number works out to be 129.8, but we had 135. This number works out to be 54.5, okay? And then this number works out to be 5.7. Now, of course, you wouldn't have 0.5 and 0.7 of an individual, but just bear with me. So these are our expected values. These are our observed values, okay? Now, I'm not going to go back through how to do a chi-square analysis, but hopefully you guys remember that chi-square is equal to the sum of the observed minus the expected squared over the expected. Okay, and so you can go back into your previous labs and figure that out. The point that I want to make here is that you can statistically test whether or not these numbers are close enough to say that we're in Hardy-Weinberg equilibrium, or are they far enough apart that our population appears to not adhere to the predictions of Hardy-Weinberg. And it turns out, if you worked out this math problem and you got a chi-square table, and we're not going to go through that today, but if you did that, these numbers are different enough from our predicted numbers that it appears our population does not meet the assumptions of Hardy-Weinberg equilibrium. So what does that mean? Well, it means that of the 5 things I mentioned, random mating, large population, no migration, no mutation, and no natural selection, one of those things must actually be happening in our population. We must have either non-random mating, or maybe our population is small, or maybe there's some migration, maybe there's some mutation, or maybe there's some natural selection going on, which kind of makes sense since we're talking about a disease. Something is happening that is causing our observed genotypic ratios and observed genotypes, genotypic frequencies and observed genotypes to be different than what we expected. So let's talk a little bit about what happens in populations when you violate assumptions of Hardy-Weinberg equilibrium. First of all, let's talk about one of the first assumptions I mentioned, and that is random mating. And so what do I mean by random mating? If you truly have random mating, then what happens is this individual has an equal probability of mating with any other individual in the population. So any of these individuals, you could pair up any of these triangles and purple squares and pentagons that are red. Is that pentagon? Yeah, pentagon. So that would be random. But the truth is, oftentimes we don't see that in nature. We often see something instead called assortative mating. And the root of that is the word assort, assortative mating. In assortative mating, individuals show a preference, okay? They don't randomly mate, they pick someone. And so in positive assortment or positive assortative mating, individuals tend to select individuals that are like them for some trait. So for example, that would be like if tall people consistently mated with tall people. Or if you're talking about, say, cats, maybe black cats consistently mate with black cats, okay? There's some trait that the organisms are selecting for and they're mating with individuals like themselves. In negative assortative mating, they're mating with individuals, they're seeking out individuals, actively seeking out individuals that are different from them. So that would be like if tall people always were preferentially mating with short people, okay? Or black cats were always mating with orange cats, okay? So we tend to actually in nature see some degree of assortative mating. Organisms tend to select mates based on traits. So it's not typically random, okay? So Hardy-Weinberg equilibrium is a best case assumption, isn't it? Now, another way that we can violate random mating that we see often in nature, whoopsie, is a special case of non-random mating called inbreeding. You've probably heard of it. The opposite of inbreeding would be outcrossing, right? If you're inbreeding, then you have individuals that are genetically related to one another having offspring. Outcrossing is when you have individuals that are not related to one another having offspring. Now, the problem with inbreeding is that it tends to concentrate, and I said I have heterozygosity here, boop, 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 that's wrong, guys, increases homozygosity. That is a typo on my part. Okay, so inbreeding tends to increase homozygosity. Well, what do I mean by that? Let's look at this example, okay? And let's say that big A is your normal dominant allele and little a is a recessive allele and it happens to be problematic. Maybe it is some disease or something like that. Okay, so in this example, we have a carrier, a heterozygous carrier, who's healthy because she's heterozygous, okay? And she's mating with a homozygous individual, and they have some babies, okay? Some of their babies are carriers. Well, if there is inbreeding that occurs, do you see how you've now concentrated this deleterious allele versus if you have some outcrossing here, you have an individual that's normal, okay? So this is problematic, this increased homozygosity, okay? Because it can concentrate disease alleles. So as I sometimes do, I'm going to go ahead and show you a video. Alleles. All right, I'm going to show you a video. I've given you the link here, but I'm going to start it at minute 136, and I'm going to go ahead and shift my screen share for you. Oops, here we go. And let's see here, new share, desktop 2, share. I'm on the right one, boom, desktop 2, great, okay. And
problem in the first place? Well, let's look at an example. So Tay-Sachs disease is an autosomal recessive disorder. And what that means is that people with no copies of the genes are unaffected by the disease. And I've drawn these people in blue. People with just one copy of the gene are not affected by the disease, but are carriers for the gene. And I've drawn these people in red. And people with two copies of the gene are affected by the disease, and I've drawn these guys in purple. So let's say we have someone who's a carrier for Tay-Sachs. So he has just one copy of the gene. If we're looking at the general population, we can see that the odds of the person choosing a mate that's also a carrier for the disease are pretty low. And if he eventually has some kids, none of them will be affected by the disease, and only a few will even be carriers. It's likely that the copies of the gene will be so spread out among the population that it would be quite rare for two carriers to actually end up mating together. Now, if we look at an inbred population where a bunch more people could be carriers for the disease, the chances of our guy choosing a mate that's also a carrier are a little higher. So more of his children will be carriers for the disease, but there's also a chance that some of his offspring may get two copies of the gene and actually be affected by the disease. Now, we just talked about an example with an autosomal recessive disorder, but maybe you're wondering how inbreeding affects autosomal dominant disorders. Well, let's look at Huntington's disease, which is autosomal dominant. And since this disease is autosomal dominant, if a person has no copies of the gene, they'll be unaffected by the gene, and I've drawn these people in blue once again. However, if a person has either one or two copies of the gene, then that person will be affected by the disease either way. And I've drawn both of these people in red. The key difference in this case is that no matter who the guy has children with, even if that guy just has one copy of the Huntington's gene, there's still a chance that there will be children affected by the disease. Now, of course, if our guy has children with someone who was also affected by the disease, then more of his children would be affected, but there's still a chance either way. Now, one of the other reasons why we're less concerned about inbreeding affecting autosomal dominant diseases is that carriers for dominant disorders are generally aware that they're affected and are well aware of the risks of them having diseased children. With recessive disorders, carriers usually don't have any symptoms at all, and they may not even know that they're carriers until they've had a diseased child. And this makes it much more important for people in inbred populations to seek genetic counseling so that they are aware of the risks of them having diseased children. So, what did we learn? Well, first we learned that certain inbred populations can have many more individuals that may carry a diseased chromosome than the general population. But we also learned that this is mostly a concern with autosomal recessive diseases, since those generally go more unnoticed than dominant ones do.
Okay, folks. So that's where I'm going to end this particular lecture, and I'm going to pick it back up. I'm again trying to break this into chunks that are a little bit digestible for you. So I'm going to stop this one, and we'll start up again, finishing our discussion of inbreeding and the remainder of the assumptions of Hardy-Weinberg. Okay, bye-bye.